Okay, in this video we're going to learn how to derive equations. That is, we're going to create situation-specific equations from fundamental equations using algebraic substitution. Now, some other phrases you might hear things like derive an equation for x in terms of y and z. Or you might hear the phrase derive an expression for x in terms of y and z. Or you might even say make a function or make x as a function of y and z. All of those would be the same way of saying to create or derive an expression. And when you finish this series of videos, you should be able to know some of the basic hints and guidance for deriving equations. And you should be able to do some simple deriving, but of course much more so once you have practice. All right, so we're going to start with some simple equations that we already know from physics class, some fundamental equations. Fundamental means the most basic. These are ones that have been found through experiment or by definition. And so the two that we're going to start with here, the definition of acceleration and the definition of average velocity. I'll also remind you that the average of the velocities is the average velocity if the acceleration is a constant. All right, so let's go on and take a look at our first derivation. Actually, first we're going to do some hints for deriving. You want to start with a backbone equation into which you're going to sub out other variables you don't want and sub in variables you do want. Any variables that has a value of 0, you're going to substitute 0 in for them, but do not substitute any other numerical values, even for things that are constants, like the number 9.8 you'll run across at some point. If you are not explicitly stated, you are allowed to have in your final derivation physical constants that are reasonably universal. Another hint, if the situation involves multiple concepts and a chain of events, it's sometimes easier to write out applicable equations for each segment and then connect them together. And then last, simplified expressions are better than non-simplified expressions. Let's see how all of that works. All right, so our first derivation is this. We have a rock that's dropped from a bridge from a height h. So here's our bridge. We have a rock. And this height here is h, and the rock goes from there down to the water. Let's call that point A and that point B. All right, and we want to derive an expression for the speed of the rock in terms of the height of the bridge and the acceleration of the rock. All right, so our first hint was to start with a backbone equation. And so I'm going to use as a backbone equation an equation that has what we want, which is the speed of the rock. So the acceleration equation up there has that, vb minus va over the time from A to B. That has the thing we want. Now the first thing I'm going to do after writing that down is realize that if the rock is dropped, then the initial velocity VA is 0, and one of my hints is to sub out any values of 0. And so I'm going to do that right now and just change this. That we can drop out because it equals 0. So then this becomes VB over the time from A to B. Now we can rearrange this if we want to write VB equals A times the time from A to B, but we're not supposed to have the time in here. It's supposed to be in terms of the height of the bridge and the acceleration of the rock. So ultimately, we need to get rid of this so we can leave the acceleration in. Now to get rid of this, let's go over and let's write down another fundamental equation that we know has the value time in it, and that's our displacement equation. That's the time from A to B, and this is the average velocity from A to B. Now, this is also equal to the average of the velocities, VA plus VB over 2, if the acceleration is constant, which we assume that it is. And again, that value equals 0, so we can drop that out. Now, what you see then is if I take just this part of what I've written, and I rewrite that, then I can say delta x over the time from A to B is equal to VB over 2. And that's helpful because ultimately I want this time from A to B. So let me rearrange this algebraically to say time from A to B is equal to 2 delta x over VB. All right, now if you don't follow the algebra, try pausing the video and reworking this until you get it like that. And the reason I want it like that is because I want to take this stuff here. I want to substitute that in for the time because I'm not allowed to have the time in my final expression, only the height and the acceleration. So let's do that substitution. That will equal acceleration times 2 delta x over VB. All right, now we're actually in pretty good shape. We're allowed to have the height of the bridge, that's delta x. We're allowed to have the acceleration, and we want VB. So this has all the variables we want and no variables we don't want. So our only next step is to simplify and to make sure that we have the right variable letters, the right symbols in. So to simplify, we only want each variable to appear once if possible, and VB occurs twice. So let's multiply both sides by V, and then we're going to get VB squared equals let's get rid of that. Okay, so this is going to be VB squared equals, and then this is going to be 2A, 2 delta, and then let's put the H in there because it's supposed to be the height of the bridge. And then finally, we can take the square root and say VB equals the square root of A times 2 times H. And that's our final derivation. So we start with a backbone equation. We substituted 0 in for any values. We didn't substitute any other numbers. We didn't have any universal constants. It didn't seem to contain a multiple chain of events, and we remembered to simplify. So again, following these hints can be useful. Now let's take a look at another derivation. All right, in this situation, a car is driving down the road at some speed we don't know when it passes a sign. When it gets to the sign, it starts to speed up, and it speeds up all the way to the second sign. So right here, accelerates from sign to the next sign. But the condition of this problem is such that the speed of the car at the second sign is twice the speed of the car at the first sign. In other words, VB is equal to 2 VA. All right, if we call this point A and this point B. And then what we're supposed to do is find an expression for the distance d between the two signs in terms of the acceleration of the car and the time it takes to accelerate between these two signs. All right, so we're actually not allowed to have in our expression any velocities. All right, so let's go about seeing what we can do here. We want an expression for distance, so that's going to appear right here. So I'm going to use my backbone equation. This average velocity equals the displacement or the distance d over the time. Okay, and let's call it time from A to B. That's the average velocity from A to B. And let's remember that that is also equal to VA plus VB over 2. But we have this condition right here. And so let's take VB and replace it with 2VA. So we have VA plus 2VA over 2. And now I'm going to simplify this. Remember, we want this part and this part. So this is going to be d over time from a to b is equal to 3va over 2. Let's rearrange this a little bit to get it just d, 3va time from a to b over 2. Now that's a good start, but that has the velocity at a and in there, and we're not supposed to have that in there. So let's try to get that out of there by bringing in the acceleration equation. Put a line here. Acceleration, this will be vb minus va over the time from a to b. And then again, let's substitute this condition up here, which says 2va is equal to vb. So 2va minus va over the time from a to b. And then let's continue on. That's just va. So a times time from a to b is equal to va. If you want to pause the video and see if you can rework this to look like this, I followed all the algebra rules, so I know it'll work. And I'm going to take this stuff here, and I'm going to sub it in for VA there. So that's going to look like D equals 3 times A times time from A to B times time from A to B. And this stuff in here is what I substitute in for VA, and that's all over 2. And lastly, I want to simplify again. Simplify means, among other things, a term ideally shouldn't appear twice. And we can make that go away. So this is going to be 3/2 a times time squared. And there's our expression that we were asked to derive, the distance between the signs in terms of the acceleration and the time it takes. And again, we started with a backbone substitution. We substitute any zeros in? No, we didn't, but we did substitute this expression which related two variables. We had no constants, and it wasn't really a multiple chain of events, but we did have to simplify. So again, not always do we use all the hints, but many of the hints we'll use. Let's go on and try one more derivation. All right, now in this derivation, this is a little bit more complicated. This one is a chain of events. So we have this box that's bopping back and forth like this, kind of around this middle line right here. If you imagine kind of a middle line like this at the x, it's bopping back and forth like this. And at some point on its way back out this way, it breaks free of the spring and it coasts all the way along here, slides a distance d before it comes to a stop. Now, our goal is going to find a formula for that distance d in terms of the givens. And what we're given, if we read the problem, is that a box of mass m is being pushed and pulled by a spring with a stiffness of k, such that it oscillates around a point x in a range of 2r. In other words, it kind of goes back and forth about that distance 2r there. Now I'm going to introduce a new formula. You don't need to know this formula, but I'm just going to use it as an illustration of a situation that has like one event and then another event, sort of a chain of events. Because one of my hints here is sometimes it's easier to write out applicable equations for each segment and then connect them together. And I want to be able to show you that. All right, so let's start with the thing that's going to connect them. And what I realize is that as this thing breaks away, it's going to slide this way. And the faster it's moving, the further it's going to slide. So when I look at this new spring formula over here, I realize that what I care about out of this is not the mass of the thing or the stiffness or this range it's oscillating under, but rather the speed at which it's going. Like that's what I want to know before I go on to the next part. So I'm going to rearrange this for the speed it's going v. And again, I'm going to let you stop and do the algebra if you'd like. But that ends up looking like this, the square root of k over m times r. Okay, that's the formula out of it. This relates the velocity of that box or the speed of that box in terms of these things. So that's kind of the first segment right there. And then there's this other segment where it's sliding to a stop. And there we're trying to figure out the distance it goes. So again, I'm going to come up here and I'm going to use the only formula of my fundamental formulas I have now that has distance in it, which is the average velocity formula. So I'm going to rewrite like this. Average velocity equals delta x over delta t. And that's going to equal VB or VA plus VB over 2. And I'm going to take just a second to get this mess out of our way here. Let's shrink this thing down. We'll put it up over here. Okay. All right. And then now that we've written that expression out, let's do a little substituting. Let's substitute out the delta x. Let's put in the d there because we want that. I'm just going to call time t. And then we know VB is 0 because it slides to a stop. So that's going to be VA over 2. And then I'll just remind us that this point A and point B, this is really the velocity at point A, that spot right there. Okay? So now what I'm going to do is rearrange this thing. It's going to look like this. D equals VA times T over 2. And now I want to get all of this stuff in here because I want to have D in terms of the givens that are up here, which doesn't include time. So let me make that substitution. This is going to be the square root of K